Why, hello friends! Jen Foxbot here for another edition of Math Mondays. Ba-ba-da-ba-ba. Yeah! Alright! Switching up my theme song a little bit so that I can keep you on your toes and keep myself entertained. Most important things, right? Anyway, so in this video we're going to continue our Algebra II exploration and dive farther into matrices. Yeah! Matrices! Why are we talking about matrices? Well, two main reasons. The first is that they show up all the time. I cannot tell you how many classes in physics and engineering relied on matrix multiplication and other concepts in linear algebra to solve really complex and difficult equations. You can't get away from them. And in fact, I was chatting with a friend that I know that makes VR games, and he was telling me how he uses matrices all the time. Every single object in a video game, especially in 3D video games, uses a matrix to keep track of how that object changes over time and how it interacts with other objects. And actually matrices are also used to calculate how the graphics change. So every single pixel is calculated using a matrix, which is super cool. And the second reason we're doing matrices again and diving into them deeper is because matrices can be tricky, and it really helps to understand what they are and how they work if we're going to use them to wield their powers and solve equations. Yay! Okay, so last time we did a general overview of matrices, and in this episode we're going to talk about three things. We're going to talk about the determinant in more detail. We'll talk about calculating the inverse of a matrix, what that is and what it looks like. And then finally, we'll end with using matrices to solve systems of equations, aka if you have more than one variable and you have multiple equations and you're like, what are these variables? Let's calculate that. We can use matrices to make our lives easier. All right, so first of all, determinants. Here we go. So let's say we have a matrix A comprised of elements A, B, C, and D. So this is a 2x2 matrix. Then the determinant of A is defined to be AD minus BC. Cool. So why do we care about this? This seems like a random equation when you first glance at it, but it's not. Haha. This equation gives us a lot of information about what A looks like. So, for example, if A, or if a matrix has all of the same elements, we're going to get a determinant of 0. What does that look like? Well, let's say I have a matrix B of 1, 1, 1, and 1. Whoops. Okay, so then the determinant of B is going to be 1 times 1, which is just 1, minus 1 times 1. Look at that! It's 0! Ooh, that's interesting. So if we have a matrix and the elements are all the same, the determinant is going to be 0. Let's check out another example. Let's say we have a matrix with the same rows, 1, 2. Then the determinant of C is going to be 1 times 2, which is 2, minus 2 times 1, which again is 2. Oh, check it out! It's 0 again! What? It's almost like there's a pattern! Haha! And lastly, what if we have a matrix where we have the same columns? Then determinant of D equals 1 times 2 minus 1 times 2. Look at that! 0 again. Haha. So the determinant tells us if our matrix has the same elements, if every element is the same. Oh, my face got blurry. Sorry about that. It also tells us if the rows in our matrix are the same. And lastly, it tells us if the columns of our matrix are the same. Pretty cool, right? So there are some other useful information, other useful things that the determinant can tell us, but I'm just going to focus on this right now because those other useful things come into play more when we are learning linear algebra. Cool. So yeah, so the determinant gives us useful information, and we use the determinant to calculate the inverse of this matrix. The inverse of a matrix is the matrix in which, well, I guess let's just define it first, because that helps. Okay, so the inverse of a matrix is defined to be 1 over the determinant times the matrix that's kind of reassembled. And so how you do that is you swap A and D, and you put a minus sign on B and C. Okay, so you might be like, what? Like my dog when I ask him a silly question, or if I'm like, do you want a treat? And he's like, oh, yes, what? What are you talking about? I'm interested, but I don't understand. So this might seem like gibberish, and again, like the determinant may be a little bit arbitrary, but that's why it helps to understand what the inverse is. So when we multiply A by its inverse, we get a matrix where the diagonal is 1, I guess with just a 2 by 2, we're going to get that, and all of the other elements are 0. So in a sense, the inverse of a matrix is sort of like the reciprocal of a number. So recall, if you multiply 2 by 1/2, you get 1. If you multiply 45 by 1 over 45, you get 1. So the inverse of a matrix is sort of like a reciprocal. But because our matrix, when we're dealing with matrices, we have to use different operations. We have a different way of calculating what the inverse is. Okay, cool. So now that we understand how to calculate the inverse of a matrix, we can actually use that knowledge to solve systems of equations. Yeah! All right. So, go ahead and take a screenshot if you want right now, because I'm gonna erase these definitions and they're super handy. But that's the benefit of a video, is that you can go back and pause. Cool. Okay, so now that we understand more about what the determinant and what the inverse are allowing us to do with matrices, we can use it to solve equations. So here's an example. 3x plus y equals 5, 2x minus y equals 0. Okay, so we can use matrices to represent this system of equations. We only have 2 here, but if we had more, we could do the exact same thing. So just like most of your teachers, I'm going to start with this simple example so that we can wrap our heads around it. Okay, so what we do is we use the first matrix to represent the coefficients or the numbers in front of our variables. So in this case, the first equation is 3 and 1, and the second equation is 2 and -1. And then we use another matrix to represent our variables, and finally the last matrix represents the right side of the equation. And so the reason why this works is because when you multiply the rows by the columns, you're going to get a matrix that has those 2 equations in it, equaling that. So it is effectively the exact same, it is the same equations, it's just a different way to represent it. Okay, so now we want to say, hey, how do we calculate x and y? Let's solve this system using a matrix. Yeah! Okay, so what we do is we want to multiply both sides of the equation by the inverse of this matrix. Basically because we want, it's the exact same thing that we do when we multiply both sides of our equation by 1/3 to get rid of this 3 on the x. So yeah, the inverse of a matrix, again, is like the reciprocal, and it allows us to pull out information and move it over to one side of the equation so that we can get x and y by themselves. So, okay, let's just do the example because I think it helps a lot to see it. Okay, so in this case, the inverse of the matrix is 1 over the determinant, which is going to be 3 times -1, -3 minus 1 times 2, times A swapped with D, and a negative on both of those. Okay, so that is the inverse of our matrix. And now we multiply the inverse by both sides of the equation. And we get, this is going to be -1/5, -1, -1, -2, and 3. We multiply by the left side of the equation, so we get 3, 1, 2, -1, and then our little xy matrix comes over, and we multiply the inverse by the right side of the equation, so we're going to -1/5 times -1, -1, -2, and 3 by 5, 0. And here's where I run out of space, so I'm going to have to erase the top of this. What I'm going to do is I'm going to write these up top. 3x plus y equals 5, and 2x minus y equals 0. So that way they are written somewhere. Okay. All right, and so now we're going to bring this up top, and we're going to get -1/5. I'm going to just keep leaving that out front until we can simplify it a little bit more. And we're going to multiply this matrix with this matrix. So again, I like to do the little underlining thing, especially when I'm reviewing or making sure that I'm doing this right. It helps to keep track of stuff. So rows with the columns for matrix multiplication. So we'll get -1 times 3, -3, plus -1 times 2, which is -2. That's the first element in our new matrix, which is a -1 times a. So if you remember, hopefully, assuming we do this right, we should get this equal the diagonal. Yeah, okay. So now we do the first row and the second column. So -1 times 1 is 1, times -1 times -1, whoops, -1, haha, forgot my sign, plus 1. Ah, here we go. So this is looking good so far. Okay, and now we do the second row times the first column. So -2 times 3 is -6, plus 3 times 2 is 6. Huzzah! That's a good thing. We'll get a 0 here. And then -2 times 1 is -2. And 3 times -1 is -3. And then again, x and y equals, and now here is the interesting part of the equation, because we don't know what this will give us, so let's calculate it. So we get the -1/5 out front. Again, let's just leave that where it is. Oh, we're gonna run into the smiley face. Oh, so sad. I'm gonna erase that. Okay, so rows with the columns. Boom, here we go. -1 times 5 is -5, and I like that we have a 0 here because that makes our life easier, because that's just gonna be plus 0. And there's only one column, so we're gonna get 2 rows but 1 column. So then the second row times the first column, or only column, is going to be -2 times 5, which is -10, and plus 0. Boom! Okay, so let's keep this -1/5 out front and just simplify this. So -3 minus 2 is -5. -1 plus 1 is 0! Yeah, we did it right! Woo! -6 plus 6, again, is 0, which is exactly what we want. And then we bring over x and y. -1/5 times -5 and -10. And actually, now I'm going to pull in the -1/5. So -1/5 times -5. Ooh, look at that. Reciprocal came in handy. So that's going to be a positive 1. -1/5 times -10 is going to be a positive 2. Rad. Okay, and the last step is to bring in this 1/5, -1/5, so that we get our diagonal matrix, and I'll show you why that's powerful. So we'll get 1, 0, 0, 1 times x and y equals 1 and 2. Yes! This is exactly what we wanted, because check this out. When I multiply this, by x and y, we're going to figure out what these variables are. So, rows with the columns. Oh, look at that. X plus 0 and 0 plus y equals 1 and 2. So, what this tells us is that x equals 1 and y equals 2. Boom! Like a boss. So, it might seem like this was a lot of work for two variables, because especially for this equation, you could be like, well, why don't you just solve for y and then substitute that in the second equation? Yes, you can also do that, not a problem. And since this is only two variables, it might have been a lot faster to do it that way, especially if you're more comfortable with that. Like in most math problems, there are many ways to solve things, and the trick is finding the easiest and quickest way to do it for your own brain. But what I want to show you is just how powerful matrices are when you use them to represent systems of equations. Imagine you had 100 variables and 100 equations that you had to calculate. That would be a huge pain. Even if you were coding that, it's going to take the computer a very long time. And so if you're talking about calculating pixels on a screen to display graphics, that doesn't really work because your user is going to have a really slow refresh rate, which, as we know, is really annoying. When I get that loading screen on Zelda, I'm just like, oh, I get it. I appreciate they put tips in there, but still, you want to get to the game as fast as possible, right? So a much, much, much faster way to calculate large systems of equations, like if you have 100 different variables, is to use a matrix. Because you do the same steps, you're just working with a bigger matrix. And because computers have a lot more, well, I will say paper in quotes, it would be a huge pain for us to write out on 100 long matrix, but it's pretty trivial to code it, right? Because you only have to code it once. And then the computer will calculate the determinant, it'll calculate the inverse, and it'll run through the simplification, and it will give you those 100 variables, the answer, all at once, which is awesome and a way better approach than substitution. So the trick is using the right tool for the right job, and when you're dealing with a lot of different variables and a lot of different equations that change a lot, especially when you're talking about video games, matrices are the way to go. All right, so thank you very much for watching. I'm going to end it there. Please let me know if you have any questions about the things that we've talked about or worked through in this video. The one thing I want to end with is to give you a problem to solve. So it's like fun homework. Yay! And let's see, negative 3x plus y equals 10. Okay, so I would want you to use matrices to solve this and tell me what you get. All right. So let me know if there are any other math topics that you're curious about and would like to cover. And otherwise, I will see you next time. Bye!